Hi everyone, this lesson is going to be an example here of a related rates of change problem. So we have car A at the top of the diagram travelling south at 40 kilometres per hour. As soon as we see a unit like kilometres per hour, we realise we're dealing with a derivative, a rate of change. And car B is travelling west in this direction here at 60. Now, for some strange reason, they've decided to label the vertical distance as x and the horizontal as y. That's no bother. We can deal with that. They're both travelling towards the intersection. At what rate are the cars approaching each other? When A is 1.2 kilometres and B is 0.5 kilometres from the intersection. In other words, at what rate are they approaching each other means at this direct line Z. Z should be shrinking as they're getting closer to each other. So we're after dz dt. That's what we really want. Now the difficulty with this one is that z squared equals x squared plus y squared from the Pythagorean theorem, if we assume this is a right angle. And z does not just depend on one variable. Z depends on both of them. So if I want to find dz dt, I really need to find the time derivative of this entire equation. So let's find the derivative with respect to time of z squared and the derivative with respect to time of x squared and the derivative with respect to time of y squared. Now each of these are taking a derivative of a variable x, z and y with respect to t. Each of these is an implicit differentiation. So the derivative of this looks like 2z, but because we were using a different variable, we have to put dz dt. This will be 2x dx dt, and this will be 2y dy dt. The 2's can all cancel very nicely. Divide by 2, divide by 2, divide by 2. And then the rate of change of z with respect to time, I'll divide by z. So it's dx dt by x over z plus dy dt by y over z. Now, fortunately, I think we have the information for everything on the right-hand side of the equation. We were told that x equaled 1.2, y equals 0.5. Using Pythagoras and recognising a 5, 12, 13 triangle, we would say that z equals 1.3 kilometres, y was 0.5, and z was 1.2. Furthermore, we've got that the car A is travelling south at 40. X is decreasing. Then dx dt is negative 40. Y is decreasing at the rate of 60. dy dt is negative 60. Those are all the things we need. We said dx dt was negative 40 kilometres per hour. X was 1.2 kilometres. Z 1.3 kilometres. dy dt was negative 60 kilometres per hour. Y equaled 0.5 kilometres. Z was 1.3 kilometres. The distance units cancel on these ratios. We'll end up adding together two things that are both kilometres per hour. It's important when we add terms that they have the same units. So let's just do a quick calculation here then, shall we? I need negative 40 by 1.2 over oops, I did that already, 1.2 over 1.3, 1.3, yep, plus negative 60 by 0.5 over 1.3. Oh, I'm hitting the wrong buttons today. 1.3, there it is. The answer is negative 60 kilometres per hour. Now, to illustrate this scenario, I just thought I would use this little GeoGebra worksheet that I've made up. So we can see here that I've got point A and point B to represent the cars. I've drawn a line segment in between them, and I've had GeoGebra calculate the distance. So when this is 1.2, this is 0.5. It's the old 5, 12, 13 Pythagorean triad. Now, I have a slider up here, and as I move the slider, let me just use the keyboard because the mouse is a little bit touchy. As I use the slider, point A and point B move according to these little functions here. So point A always has an x-coordinate 0. It starts at 1.2 and it's decreasing at the rate of 40 times time. This time is in hours, and I'm stepping forwards in increments of 1/3600th of an hour, or increments of 1 second. So let's just step forward by 1 moment. You can see there that the distance between A and B is actually a little bit less, isn't it? Now, a moment ago it was 1.3, now it's 1.28. If I were to calculate on average across that 1 second, what would I need to do? Well, my distance is now 1.2834. It used to be 1.3. So the difference is there. And what was the time step? The time step was 1/3600th of a second, of an hour. In other words, a second. So in 1 second, on average, look at that, minus 59.76. Why isn't it exactly the same? Well, because that was an average speed across a small time of 1 second, not an infinitesimal time, dt. The correct value for this answer, which is when car A is here and car B is here, then it is exactly 60 kilometres per hour that they are. The length of this line is decreasing by exactly 60. A moment later, then it would be different. So, as you can see here, the cars keep moving forwards. Distance is now increasing. So the velocity of approach is continuously changing as the cars continue to move. And of course, there's no chance of a collision. Look at that. By the time car A gets to the intersection, car B is 1.3 kilometres west of the intersection. So there's no danger of any problem like that. That was an interesting question. The main reason I wanted to demonstrate this one was that we had here a variable z, which was a function of 2 other variables, because both x and y were changing. And when that's the case, it's easier sometimes just to use implicit differentiation to solve these. Okay, thanks for watching.